So welcome to this morning session. Our first speaker this morning is Vadim. He will continue his story about Poisson boundary.
Yeah, okay. Thank you very much for the introduction. So yeah, indeed, it's a long story. So let me, as yesterday, remind you of the highlights of the previous episode. Now our setup is the following. We have a countable group. We have a probability measure on this countable group. And we consider the associated random walk. So that's the random walk. Okay, now we're interested in the non-trivial, stochastically significant behavior of this random walk infinity, and this behavior is described by the Poisson boundary, which is determined as the quotient of the path space, which is defined as the quotient of the path space determined by the exit sigma algebra. Then the Poisson boundary is the quotient of the path space determined by these exit sigma algebra. So that's this quotient is defined in the measure category. It's not a topological space, so everything related to this space is defined modulo 0, modulo subsets of measure 0. And this space is endowed with an action of our group G. This measure satisfies the following stationarity condition. So that's what's called harmonic measure. And it satisfies the stationarity condition, namely the harmonic measure is the average of its translates, taken with the weights determined by the step distribution of our random walk. And then this property implies that if we take any measurable, any bounded measurable function on the boundary, then one can define the associated function on the group just by integrating our boundary function with respect to the corresponding translate of the harmonic measure. And then this is the Poisson formula. This is the Poisson formula because it establishes an isometric isomorphism between the space L infinity and the space of bounded harmonic functions. So conversely, how does one recover the boundary function from a harmonic function? In the following way. By the martingale convergence theorem, I denoted by, look at the G. By the martingale convergence theorem, which is applicable here because the martingale condition is precise for this, precisely the harmonicity condition on our function f. This sequence converges almost everywhere. So let me denote this limit by f hat. Then this is a function of our sample path. Oops, converges. This is a function on our sample path, but obviously if we shift our sample path or change its initial segment, then the limit remains the same, and therefore this limit is measurable with respect to the exit sigma algebra. Or in other words, it means precisely that this is a function on the Poisson boundary. So in one direction, we just write the usual Poisson integral. We have a family of measures parameterized by the points inside, by the points from our state space, which in this case are just the translates of the harmonic measure. If we integrate it against a certain boundary function, then we obtain a bunch of values which we can consider as a function inside, as a function on our group, and this function happens to be harmonic. Conversely, if we have a bounded harmonic function, then by taking its limits along sample paths, we obtain the corresponding boundary function. Okay, so now the following questions arise. So first, the question about the identification. Of the Poisson boundary. And a particular case is the question about triviality. It's a particular case of the previous question because here we just want to make sure that the Poisson boundary is a single point space. So we want to identify it with a single point space. And then I started to talk about various examples of the boundary behavior just to provide a certain context to what is happening. So there are basically the following examples of the boundary behavior which we currently know or have been known until recently. So the example number 0 is when the Poisson boundary is trivial. And I have changed the notation, sorry. I should denote it like this. Yeah. So, so the example number 0 is an example when the Poisson boundary is trivial, so that we are able to identify it with just one point set. We're able to show its reality. And we already have one example like this, very basic example. That's a situation when our group is just a group of integers, and the transition probability measure was also very simple. Let's say it was charging just the cyclic generator and its inverse. Okay, so in this case, one can directly see that all the harmonic functions are just linear functions or affine functions, be more correct to say, and therefore the only bounded ones are constant. Only bounded ones are constant. Question? Okay, then the second class, or I denoted with number 1, is hyperbolic behavior. Hyperbolic behavior, more specifically, we had already an explicit example like this. So here, if one takes for G the free group and for mu the uniform measure on generators, let's say 2 generators, then our random walk amounts just to the simple random walk on the Kerr graph, simple meaning that the transition probabilities are equidistributed among neighbors. And here, well, it's very clear geometrically that this random walk converges to the boundary. So here we know that almost every sample path converges to a point G infinity, which belongs to the geometric boundary. The geometric boundary in this situation is very well defined. Geometric boundary is very well defined. Then, of course, one can ask the identification question. I will return to this later, but for the time being, maybe let me explain in more detail why does one have here convergence, not just for the simplest case when our random walk is the simple random walk, but actually for an arbitrary probability measure without any conditions. So this was already mentioned by Sebastian yesterday, but let me do it again. That's very nice trick, which goes back to Furstenberg. Which consists in the following. There are two ingredients in this proof. One is entirely geometrical, and the other one is entirely probabilistic. So it splits very nicely. So first, the probabilistic component. So we have our probability mu on the group, and we have the action of our group on its boundary. So here I'm talking for simplicity just about this, but this can be done in much more general situations whenever one has a reasonable geometrical boundary, satisfying certain properties, and you will see which properties one really needs here. Okay, so now so I have this geometric boundary of our group, and the first assumption that I want this geometric boundary to be compact. Then this compactness allows me to apply the Krylov-Bogoliubov theorem, or this form it's probably should attribute it to Kakutani. Anyway, we can is the following. We have a operator which corresponds to the now on the boundary itself, corresponding to the boundary action. So here we have the corresponding the Markov chain is described like this. So we sample an increment from the step distribution, which is our measure mu, but now we apply this increment not to a point of the group, but to, yeah, I should write it, we have left action. We apply it to a boundary point. We apply it to the boundary point. So now we have a Markov chain whose state space is the boundary, the space of infinite words in our situation. And now the collection of the corresponding transition probabilities, phi gamma, is continuous in the weak topology. So the map which assigns to any point gamma, the corresponding transition measure is continuous. And then under this condition, it is very well known that our Markov chain will have a certain, at least one, stationary measure. So that's, and the proof is more or less the same as in the Krylov-Bogoliubov theorem. So Krylov-Bogoliubov theorem tells us that if we have a homeomorphism of a compact space, then there exists an invariant probability measure. And here, our dynamics is not deterministic, it's stochastic, it's Markov dynamics, but the argument is precisely the same. So we have a stationary measure for this chain, and what does this stationarity mean? That's precisely the mu stationarity condition which we had on the Poisson boundary. Okay, now since I have this stationarity condition, I can write again the Poisson formula. Namely, I can take any, and now I want to work logical category. Now I take any continuous function on the boundary. And then I can write the associated harmonic function. It will be harmonic because we have stationarity. And then we know that this is a bounded harmonic function, and therefore it converges along almost every sample path. Now, what does it mean that it converges? It means the following. So the values of this function are nothing but the integrals of our test function against the corresponding translates of our stationary measure. So now what I can do the following. I can choose another function here. And I will have almost surely convergence of these integrals for another function as well. Now, I have used the word almost surely twice, because actually what I'm doing here, if I do it rigorously, I'm saying the following, that here, if we look at the space of sample paths, then we do have this convergence outside of a certain exceptional set. And a priori, this exceptional set depends on my function f. So for every function, I will have its own exceptional set. Now, however, if my space is separable, then it means that the space of continuous functions is also separable, and there I can take a countable dense subset. And what's important here is that the collection of the functions which I have chosen is countable. Therefore, if I take their exceptional sets and I take their union, I will take a countable union of negligible, of measure zero sets. And therefore, this union will still be of measure zero, will still be negligible. And now it means the following, that if I take here my function f hat from a dense family of continuous functions, then I will the convergence of these integrals. Almost surely. Now this almost surely is the common almost surely. What does it mean? Means, and now if I have this convergence on a dense family, then of course I will also have this convergence for an arbitrary function here. Now what does it mean? It means precisely by the definition our sequence of measures converges in the weak star topology. Take countable dense family of f hat. And then we conclude, therefore, that the sequence now of translates of my measure lambda converge almost fully to a certain measure, let's say lambda infinity. And here, well, I'm using probabilistic notation because, of course, this lambda infinity is not the same for all sample paths. It depends on the choose here in the same way as when we have convergence here, the limit point depends on our sample path. So we can consider this limit measure as a random measure, Okay, so that's the end of the probability part of the argument. And now there is entirely different geometrical part of the argument. Second, geometrical argument. The boundary, and this is an argument which involves a certain property of the boundary action, as I promised. The property is the following. If we have a sequence of points in our group which converge to a certain point on the geometric boundary, and we have a purely non-atomic measure, then this sequence of group elements will actually contract this measure to the delta measure at this limit point. So this, once again, there is no probability in this claim. It's, well, basically one can call it a contraction property of the boundary action. This can be and should be proved separately. That's a pretty easy argument. Now, if we combined these two parts of our argument, then immediately it implies that actually our sequence has to converge to a boundary point G infinity, and then this limit measure, lambda infinity, is actually the delta measure at this point G infinity. Okay, so here there is one little technicality which I have omitted, namely what one has to check that the stationary measure which we obtained there cannot have any atoms. But, well, that's very easy. Okay, so it shows that we have boundary convergence. Well, in particular, of course, all these conditions are satisfied for the case of the free group, but there are many, many other examples when this trick works and it provides boundary convergence. Okay, now one more example. More example is the example number 2 will be configurational behavior. Configurational behavior, and here I'm referring to a very specific group where it was first observed, that so-called lamplighter group, or rather lamplighter groups, which are defined in the following ways. That's, well, a certain Riff product, but I will avoid this terminology. I will describe it more explicitly. So suppose we are given a countable group. And we have, for simplicity, let's just take the simplest lamplighter. So we take just the group Z2, which consists of two elements, addition modulo 2. And then I consider the following semi-direct product. So I take the, let me use a slightly non-standard notation. I consider the group of all functions on the group G with the values in Z2. Or in other words, I'm considering all the configurations on my group G with values 0 or 1. And here, well, these configurations are finitely supported. And one can think about these configurations as we have a field of lamps. So we have our group G, or you can think about the telegraph of this group. And at each vertex, there is a lamp. It can be either on or off. Okay, and the condition is that only finitely many of them are allowed to be on. Okay? That's abelian group, but infinitely generated abelian group. And now the group is endowed, the group of configurations is endowed with the natural action of the group G by automorphisms. What are these automorphisms? These automorphisms are precisely the translations. So one can just move the whole configuration wholesale by applying any group element. Okay? And then one can form the corresponding semi-direct product. So what is the definition of this semi-direct product? Let me write it formally. So G1 phi 1 times G2 phi 2. The product is the following. You take the product on the first component, G1 times G2, and then on the second component, you do the following. You take the first configuration, and then you add to this configuration the second one, shifted by, in the lamplighter group. So we take the multiplication on the first component, and then on the second component, we take the first configuration and add to it the second one, shifted by the group component of the first element. Okay, so why is this group called lamplighter group? For the following reason. Let's consider the following generating set of this group. So either we take one of the generators of the first group paired with just zero configuration, or alternatively, what we can do, we can just take the identity of the group G on the first component, and on the second component, on the other hand, we can add the configuration which consists of only one lamp which is on, and that's lamp is chosen in the most symmetric possible way. That's just the configuration at the identity of the group. Okay, and let's look at what happens if we consider, for instance, the random walk whose step distribution is supported by these elements. And these elements actually can be easily seen to be generators of the lamplighter group. Okay, so then if we look at this multiplication formula, then what happens here? So I consider my random walk. Therefore, I start from a certain point in the group, which is a pair of these configurations, which is a pair of these elements, and then I multiply by one of these two increments, by one of the increments of these two kinds. Okay, so then what happens? If I multiply by the increment which is of the first kind, then what happens? Okay, let it be HT. Then what happens? I multiply the first coordinates, GH, and then what happens with the second coordinate, with the configuration? Here I have to take my original configuration phi plus the corresponding translate of the configuration in the second argument. But this is the empty configuration, and therefore its result of its translation will also be an empty configuration. And therefore, finally, the result of this multiplication is just shifting the group component of our position by H and changing and doing nothing with the configuration. Okay, now, if I have my increment of the second type, then what happens here? So first coordinates, I do the usual multiplication, which means that I don't change the first component. Whereas on the second component, what happens? I take the configuration phi, and I add to this configuration. Now here in the second multiplier, the configuration component is non-trivial. So I have to take this configuration, delta E, and shift it by the element G. But the result of shifting this configuration where the lamp was at the identity of the group is precisely the configuration where the lamp will be at the point G. Therefore, we can really describe our random walk as the following process. We have two components, the group, which can be interpreted in the following way. So the first component is a group element. So that's a position on our group, and we can think about it as the position of the lamplighter. And then the second component here is a certain configuration of lights. And then our random walk in these terms becomes very natural. Namely, what do? Either the lamplighter moves without changing the configuration, or alternative, if we choose as our increment this one, then the lamplighter does not move. It remains at the same position as at the previous moment of time, but instead the lamplighter changes the configuration at the point where he stands. In other words, if the lamp was on, it now becomes off. If it was off, now it becomes on. Okay, so now suppose that our group G is such that, for simplicity, the simple random walk on this group is transient. Then what does it mean? It means that our lamplighter, this person with the who changes the state of the lamps, eventually will go to infinity. So for instance, if our group is the three-dimensional lattice, then this is the case by the famous Poisson theorem. So the simple random walk is recurrent in dimensions 1 and 2, but it's transient in dimensions starting from 3. Okay, so our friend lamplighter eventually escapes to infinity and never returns. which means that he leaves behind a certain landscape, a certain pattern of lamps, which cannot be changed infinitely many times, right? Because they can only be changed when the lamplighter is there, but he's gone. So ultimately, what do we get when the lamplighter is gone to infinity? We are left with a certain collection of lamps which are on, and the other ones are off. So this gives us an example of a non-trivial behavior at infinity. So in this case, the Poisson boundary is also non-trivial. Okay, so now I want to specialize my position. So what do we have here? We have three examples of boundary behavior, which are trivial boundary behavior, one hyperbolic, non-trivial, and two is configurational non-trivial. So here, as I have already said, the main problem is that if we want to complete our study, we want to make sure that examples of the non-trivial boundary behavior which we observe actually describe the whole Poisson boundary. We want to make sure that there is nothing else left. And in the overwhelming majority of situations, when it has been done, so here, for instance, free group, that's the most standard example, or hyperbolic. Or here, just for the lamplighter, over, let's say, Z cube. It relies on quantitative methods, namely the identification of the boundary in these situations, and actually in almost all known situations, relies on the entropy theory of random walks. So there is a criterion for identification of the boundary in terms of the entropy of the conditional chains of the random walk. It has to vanish, and it requires some calculations. Actually, to begin with, all this only works under the condition when the entropy of the step distribution is finite. This all entropy theory only works under this condition, and then, well, still, so this theory was developed by Vershik and myself, and then for the description of the boundary, that's my criteria. Then, if you want to apply them in particular situations, well, there is still some additional work, but it has been done for the free, let's say, in hyperbolic groups by myself, and that was actually the motivation for developing the entropy theory. And for the lamplighter group, that's a more recent development, about 5 or now maybe a little bit more years ago. It was first done by Anna Erschler, but for sufficiently high dimensions, starting from 5, and just a couple of years ago, Russ Lyons and Yuval Perez finally showed that in the Poisson boundary for the lamplighter groups is described by the limiting configurations. So this is what I'm not going to talk about. What I'm going to talk about is the qualitative theory. Qualitative theory, which doesn't impose any conditions on measures whatsoever, but instead it tries to characterize just the groups, just the random walks for which the Poisson boundary is trivial, or alternatively for which the Poisson boundary is non-trivial. So here we will be just addressing one question. What are random walks, or rather what are the groups on which there are random walks with a non-trivial boundary? On which groups are there random walks with a non-trivial boundary. And maybe before going into media res, let me mention one problem which is currently completely open. That's the problem of the stability, so-called stability of the Liouville property. Stability of the Liouville property. So let me remind you that the Liouville property is just another way to say that the Poisson boundary is trivial. And the question is the following. Well, actually, I have already formulated it, but I have to add more specific details. So the question is the following. Suppose we are given a finitely generated group. And we are given two finitely supported symmetric measures. We are given finitely supported symmetric measures, and of course, I want these measures to be non-degenerate in the sense that the supports generate the whole group. So for instance, one can just take two different systems of generators, add their inverses, and consider uniform measures on generating sets. The question is the following. Are the Poisson boundaries of these two measures trivial or non-trivial simultaneously? In other words, whether this property that the Poisson boundary is trivial for a finitely supported symmetric probability measure, whether this property is satisfied simultaneously for all measures or not. And in the more general context, when there is no group symmetry, let's say when we are talking about the random walks on graphs or about Brownian motion on Riemannian manifolds, In these situations, one can also ask a similar question. This would be the stability of the Liouville property with respect to quasi-isometries. When the metric is expanded, when the ratio of two metrics is uniformly bounded below and above. And in that situation, there are examples showing that the Liouville property, it's kind of not an L2 property. It's not stable with respect to quasi-isometries. However, these examples were first constructed by Terry Lines. That's another Lines, not Russ Lines. And later, a different example was given by Itai Benjamini, which was his, I think, first publication. But all these examples are essentially non-symmetric. And for groups, this question is completely open. Of course, in all the examples, we are currently familiar with these properties satisfied, namely, all finitely supported symmetric measures are Liouville or non-Liouville simultaneously. However, I personally am inclined to believe that there is no reason for this conjecture to be true, and it's just that our collection of examples is not rich enough to exhibit a counterexample. Okay, so now let me return to the qualitative theory. Return to the qualitative theory. And here there are two results which have been known for quite some time now. The first one concerns the situations when the Poisson boundary is always non-trivial. And the answer to this question is the following. So what do I mean by always non-trivial? So for any step distribution, for any random walk. And the answer is if and only if the group is non-amenable. So in fact, the notion of amenability is quite intimately related to the Liouville property. So let me say a couple of words about it. So, shall I remind the definition of amenability? Okay, let me do that. So, who are amenable groups? Amenable groups. So this is the class of groups which can be considered from the analytic point of view as a natural generalization of the class of finite groups. Namely, finite groups can be characterized by the property that on finite groups there exists a finite invariant measure. So what is this? This is just a uniform distribution on the group. And obviously, this uniform distribution only exists if our group is finite. Now, if one wants to weaken this property so that it would be applicable also to certain infinite groups, then actually one can do it in the following way. So what is a characterization of finite groups? So G is finite if and only if there exists an invariant probability measure. So what is an invariant probability measure? That's an element from L1, let's say plus N1, so it's positive and normalized, such that it is invariant with respect to the action of the group by translation. Okay, now when I want to weaken this definition, then there are two places in this definition which I can relax. So namely, what can I do? Suppose I know that there are no invariant objects in the space L1. What instead I will look for invariant objects in a bigger space, in a natural bigger space. What is this natural bigger space? Well, that's where one can naturally embed L1. And the theory of Banach spaces tells us that this natural bigger space will be what? Will be the second dual of L1. So the first dual space is L infinity, and then one has to, because L infinity is functionals on L1, and then one has to consider pass to the functionals of L infinity. And these are, if we are talking about positive normalized functionals, these are what is known as means. So instead of this, I take L infinity star, and there I look at positive normalized elements. And this is the original definition of von Neumann. However, the kind of disadvantage of this definition is that it's not really applicable in real life, because you cannot really describe any of the objects here explicitly unless they are honest measures. So they're highly non-constructive, and therefore they're mostly useful for, let's say, impressing first-year graduate students by proving Banach-Tarski paradox and things like that. There is a much more constructive way, which actually had been known long before von Neumann, which is the following. Instead of changing the space, let it be still the space of probability measures, which we know very well, and we are talking about a countable space. But what we can relax is the following. Here, instead of exact translation invariance, we can replace it with approximate invariance. So the condition becomes the following, that there exists a sequence of probability measures on our group such that it is this sequence which is approximate invariant. So if I take this sequence, I take any group element G, I look at the translates of my measure, I shift them, and then the condition is that these measures, the original ones and the shifted ones, they are almost the same in the strongest possible sense, in the total variation norm, And such sequences had been known before von Neumann, because, for instance, how does one prove that the group Z, for instance, is amenable? Okay, so what is the sequence of such asymptotically invariant measures? Let's take the increasing sequence of intervals from 1 to n. And let us define the measure Mn to be the Cesare average of the delta measures over the points from this interval. Then this sequence of measures indeed asymptotically invariant. That's an easy exercise. And this is precisely the reason why Cesare had introduced this sequence, because he wanted to make why he introduced these averages, because he wanted to make convergent certain sequences which wouldn't converge otherwise. So it improves convergence. I have erased this part such. Okay. Now I should say amenable. Yeah. Okay, I replaced the second line, but not the first. Okay, so now amenability, once again, it's the existence of an approximately invariant sequences of measures. Now, how is it related with the business of random walks and the Poisson boundaries? So, if we have our random walk, then its position at time n, if we start at time 0 from the identity, is the product of n increments. Where in the probabilistic language, each of these increments is distributed according to the measure mu, and they're all dependent. So that's independent, identically distributed random variables in the probabilistic language. And then, when we take their product, the distribution of this product will be precise what is called the convolution, or rather n-fold convolution power of the measure mu. And now let's, instead of an arbitrary sequence of measures Mn here, let's specialize. And let's consider the sequence of these convolution powers. Let's consider the sequence of these convolution powers. And let's assume that this sequence is asymptotically invariant. Then what does it mean in terms of our random walk? It means the following. So we start from the identity. It gives us distribution, which is the n-fold convolution of the measure mu. And if we start from the identity, from the element G, then it gives us the shifted measure. Now, if we have a harmonic function, then by definition, harmonic function has the mean value property with respect, not mean value, how is it called? Is it called mean value property? Well, anyway, if we average harmonic function with respect to the transition probabilities, then we recover its value at our starting point. And of course, we can do this averaging many times. Therefore, if our function is harmonic with respect to the measure mu, it is also harmonic with respect to the n-fold convolution. Okay, and then what do we have? So the value of our function at the identity will therefore be equal to the result of averaging this function with respect to the n-time transition probabilities issued from the identity. Okay? In the same way, if we start from another point G, then we have to average with respect to n-time transition probabilities issued from this point. But these transition probabilities are just translates of the transition probabilities issued from the identity. So that's the sum over with the same coefficients of the value x at of the values of our functions at the points gx. Or I can write it in a different way. So namely here I'm averaging the values of my function over the measure mu n of x, and here I'm averaging with respect to the translated measure. However, these two measures almost coincide. These two measures almost coincide. And since my function was bounded, it implies that actually then the values of our function at any 2 points, the identity and the point G, have to be the same. They have to be the same. So if one has this property, then the Poisson boundary is trivial. Then the Poisson boundary is trivial. Okay. Now, actually, one can show that here, and this is a fact which is true in full generality, not just for random walks on groups, one can show that the converse implication is also true. Namely, the triviality of the Poisson boundary just means that the n-step transition probabilities asymptotically do not depend on the starting point. Not depend on the starting point. And therefore, the conclusion is the following. If Poisson boundary is trivial, then the group is amenable. Then the group is amenable. So this observation was is due to Furstenberg. So that's 63, or no, a bit later. Let's see, 1970. And at the time, he also asked a very natural question, what goes in the opposite direction? What goes in the opposite direction? So conjecture is that on any amenable group, there exists a measure with the trivial Poisson boundary. Trivial Poisson boundary. Of course, and Furstenberg was perfectly aware of this, if you have an amenable group, you may also have measures with non-trivial Poisson boundary. Well, at the time he was only interested in Lie groups. There, these examples are pretty straightforward. So for instance, one can take the so-called AX plus B group. So that's a group of the affine transformations. That's a group of the affine transformations. And then here, how can one exhibit a non-trivial boundary behavior? So this group is amenable. This group is amenable. How can one exhibit non-trivial boundary behavior? In the following way. Let's assume that we are only considering transformations which are contracting, or let's say contracting on the average. Then when we take the corresponding products, what happens? So this is also a semi-direct product. So here what do? We multiply the first coordinates. And then on the second coordinates, we have something which resembles the Lamplighter group. So here we would have B1 plus A1 B2 plus, yeah, so what happens for this AX plus B group, when we take these products, we have here B1 and then A1 B2, then A1, A2, B3, and so on and so forth. And then if A's are contracting, either all of them are less than 1 or they're contracting on average, then here these corresponding series will converge, and this will provide us with a non-trivial behavior. So the presence of this quantifier, of the existence quantifier here is very important, and this conjecture indeed was solved by Rosenblatt, Vershik, and myself. So theorem, therefore, which provides therefore the following characterization of amenability. Theorem. Group G is amenable if and only if there exists a probability measure on the group G, which is non-degenerate, so one can even assume that its support is the whole group G, such that the Poisson boundary is trivial, such that the Poisson boundary is trivial. So, yeah, sorry for interruptions. I don't think I have enough time to start talking about the proof of this theorem, so maybe I will then do it at the next lecture tomorrow.
Thank you. Any questions or comments?
There is a question.
Can you explain how this measure looks like, say, on the Lamplighter group? Can you explain how this measure, which gives a trivial Poisson boundary, looks like on the Lamplighter group? Because on the Lamplighter, you explained that you have this set of configurations. It looks like the Poisson boundary should always be non-trivial, but to explain here, you can make it trivial.
Okay. Yeah, that's a very good question. So, yeah, the Lamplighter group, it is amenable. It is amenable. However, yeah, the Lamplighter group is amenable, and therefore, according to this theorem, there should be a measure with trivial boundary. There should be a measure of trivial boundary, but indeed, I have kind of explained to you why the Poisson boundary is non-trivial. So what's the trick here? The situation is the following. So in the construction of non-trivial Poisson boundary, I was using two actually assumptions. So for non-trivial boundary, I was using first the fact that the random walk on the base was transient. And second, I was using another property of my random walk. I used the fact that the lamplighter range is finite. So actually, in the situation I was describing, the lamplighter was only allowed to change the configuration at the point where the lamplighter stands. But of course, if I allow the lamplighter more freedom and I allow him to change configurations within a certain uniformly bounded distance from where he stands, the argument will still work, no problem. However, the problem arises in the situation when this lamplighter range becomes infinite. So that one can imagine the following situation. So what do we have here? Essentially, we have two distributions because our group is the semi-direct product of the base group and the group of configurations. Okay. And roughly speaking, one can say that we have actually here two ingredients. One is responsible for working on the base group, and the other one is responsible for changing configurations. And then one can imagine the following situation, that my measure is very, very spread out. The measure on the space of configurations. So that the lamplighter, even though the lamplighter is far, he still can change lamps more or less at arbitrary distance from where he is. And the way he changes these lamps is completely random. So that at each step, he like throws a stone or shoots an arrow, and the range of this arrow is potentially unbounded. And then what lamplighter does, he completely erases any memory within the range of his throw. What does it mean? He erases all the memory. He applies a random change to any lamp. Okay, so here we would have n lamps, then 2 to the power n configurations. And now let's assume that all these 2 to the power n configurations are checked with the same weight. Okay, then after that, all the memory will be erased. All the memory will be erased. And this actually provides an example of a, that's pretty explicit example of a random walk where this argument actually shows that the boundary is trivial. So that's an explicit example of random walk with trivial boundary. So when can one do this? Actually, things like this, of course, are only possible in the situation when our measure not only it is not finitely supported, but it has a pretty heavy tail at infinity. So in particular, one can show by analyzing these arguments more rigorously that if, for instance, our random walk has a finite first moment, then everything still works as it does in the case of finitely supported measures. There is a theorem of Anna Erschler, which says that, moreover, if our measure, if our step distribution has finite entropy, then the Poisson boundary is always non-trivial, but there actually one doesn't know how to describe it, because it may so happen that the configurations don't stabilize, but at least it's non-trivial. However, if the entropy becomes infinite, then it is pretty easy to construct examples of measures with the trivial Poisson boundary, and it's roughly speaking, it is the same idea which will be applicable to showing it for an arbitrary amenable group.
Poisson boundary can be used to say distinguish between the quasi-isometric classes of the major equivalent?
Yeah, that's very good question. No, not that I'm aware of. And okay, so the situation is the following. If we want to describe the Poisson boundary, currently I will be talking about next time. So currently the situation is the following. So if our group is sufficiently rich geometrically, like a free group or hyperbolic group, then what we do, we identify the Poisson boundary with geometrical boundary. What does it mean? I have actually outlined the arguments, namely, given our step distribution, there exists a unique stationary measure on the boundary, then one can show that endowed with this unique stationary measure, the geometric boundary indeed becomes the Poisson boundary. Then we can compare the Poisson boundaries of different groups because we know that they live on the same topological space. However, the corresponding harmonic measures, they don't have to be equivalent, and typically they will be singular. Well, I'm saying typically, it's easy to say, but that's actually currently a very active topic because this conjecture had been formulated a while ago, but now finally we are at the stage when we can prove that measures are indeed typically pairwise singular. But talking about quasi-isometric rigidity, yeah, I don't think it's really applicable to this situation. So once again, my personal opinion is that we just don't have enough examples. There should be examples which would be pretty weird from our today's point of view, but would become normal once we acquire more knowledge. So I will discuss actually one of examples like this, completely unexpected, tomorrow.
And is that possible to take it symmetric, or is it?
Here, yes. I didn't say symmetric. Yeah, one can take symmetric.
Because in the example of a hyperbolic plane, you like drag all the points to
yes.
boundary point.
Okay, that's also a very good question. That's something I couldn't touch here, but since you have mentioned it. Okay, so the question is actually the following. So this example with the affine group, AX plus B, of course, it was known, and I presume it was known maybe even before Furstenberg, so that's very easy. That's a very easy example. However, if you want to do something like this with a symmetric probability measure, you won't be able to do it within the class of Lie groups. So for Lie groups, if your group is amenable, then the boundary is trivial for any symmetric measure. So it was kind of novel at the time when Vershik and me, we had exhibited this example of the lamplighter group. Because there the key difference is that in the lamplighter example, the measure can be chosen to be symmetric, which is impossible for Lie groups.
Further questions? Not, let's thank Vadim for his talk.
Thank you.